Hello, everyone. Welcome to today's Luohan Webinar. I'm Xijie, the host for today's event. So today we are very happy to have Professor Anton Korinek from University of Virginia to talk about the scenarios for the transition to the AGI. So Professor Anton, you have about like 1 hour. Please take it over. Thank you.
Thank you very much for inviting me to present in your webinar series. I'm going to share my slides. Can you see them? So this paper is about scenarios for the transition to AGI and CTI. So in the past 24 months, we have all kind of very publicly seen that AI has advanced very rapidly at a pace that by some measures has been accelerating. And the recent progress has brought the possibility of artificial general intelligence within tangible reach. So what is artificial general intelligence, or abbreviated AGI? That would be the ability of machines to perform all work tasks that humans can perform. So if we really reach artificial general intelligence, that promises significant productivity gains. But since these machines can do anything that a human worker can do, it would also imply that they can substitute for human labor. Next slide, please. So the questions that we are addressing in this paper is, first of all, if this were to really happen, what would the transition to AGI look like? There are many voices in the AI research community that say we are already on that transition path. So what should we expect economically? And what would that imply for output growth and for wages? And in particular, what a lot of people are concerned about, under what conditions would wages collapse? Next slide, please. So I'll start with kind of a very brief high-level overview of our key assumptions and then our key results before I go into the more technical details of the paper. But our key assumption is essentially that work is made up of elementary tasks, atomistic tasks. And I should emphasize, these tasks are much smaller, much more basic than the tasks that are usually used in the literature that tries to study the potential for work automation, which is oftentimes based on databases like the US Bureau of Labor Statistics ONET. And in those databases, we have tasks like college professors are preparing lectures, which is very high level, but it's very hard to kind of talk about what exact parts of that can we automate. So we dive much deeper into the different parts of task automation. And what we view as the main distinguishing characteristic is the computational complexity of different tasks. So for example, the task of preparing lectures for a college professor can be split up into, first of all, creating an outline. You can see a language model nowadays doing that already. Secondly, filling in the details of each part of that outline. Third, thinking about how students will respond to each of those parts. So we can dive deeper and we can distinguish tasks into really elementary things. And at that elementary level, we argue that tasks are unchanging. So there are certain things that human brains can do, and those things get wrapped up into job functions like being a professor or being a prompt engineer or being a doctor or whatever it is. But the fundamental underlying tasks rely on specific capabilities of our brain, and those are unchanging because evolution has made us what we are, and that's not really changing from decade to decade. That's something that's more like a process over tens of thousands of years. So the main distinguishing characteristic of all these atomistic tasks, as I mentioned, is their complexity. or as we will refer to in the paper, their compute intensity, their computational intensity. And what we then do in the paper is we consider different scenarios for the distribution of tasks in this kind of space of complexity. We call it the distribution of tasks in compute space. And one possibility that we consider is that the complexity of tasks that humans can perform is essentially unbounded. So if that's the case, then whenever we automate something, we can kind of move into the unautomated tail of the complexity distribution. And then a second possibility that we consider is that the distribution of these tasks in the complexity space is bounded, which means at some level there's a maximum complexity. Once machines can perform that level of complexity, there is nothing left that only humans can do. There's nothing left that's exclusive to us. Now, an alternative interpretation for complexity would be that we reserve certain tasks for humans, that we say, oh, machines are not allowed to be, for example, lawmakers or regulators or politicians or whatever it may be that the tasks in our distribution is about. Next slide, please. So here on this slide, I provide a graphical illustration of what these kinds of complexity distributions may look like. On the left side, you can see a scenario where the distribution of tasks is essentially unbounded. So if you look at the tail of this distribution, it extends into infinity. And what you can see in this graph is there is a vertical axis which depicts the fraction of different tasks in a complexity basket. And there is a horizontal axis which depicts how complex different tasks are. So here in this scenario that we depicted, there are a lot of tasks of lower complexity, which are illustrated in gray because they have already been automated. And then there's this dotted line, the frontier of automation in 2024. Everything to the left of this frontier can already be done by machines. Everything to the right is too complex to perform by machines. And what happens over time is that this frontier moves to the right and automates more and more tasks. And you can see in the past, we have always moved into the tail of unautomated tasks. And that's what's behind our increase in prosperity. We have focused on more and more complex things, and we have let the machines do the things that are computationally easy. So if we are indeed in this picture on the left-hand side here, then we can continue to play this game forever. We can always move into more complex things, and the economy can leave the automated things to the machines, and there will always be work for humans. However, there is a different scenario, and a lot of people in the technology space are talking about that different scenario, which may be that the tasks that brains can fundamentally perform may actually be of bounded complexity. So if we are in this scenario on the right-hand side, then in the near term, things will continue just the same way as they do in the scenario on the left-hand side. We will also automate things. The frontier will move to the right. We humans, we will reallocate into the unautomated tasks, and then that can proceed for a while. However, at some point, the machines will be able to reach the maximum complexity of tasks that can be performed by humans. And once they do that, then there's nothing left that is exclusive to humans. We have lost our special status. And at that point, the behavior of the economy may fundamentally change. We may experience a very different regime than what we have been used to since the Industrial Revolution started in Great Britain some 250 years ago. Next slide, please.
Sorry, can I ask one question?
Anybody, feel free to
so, yeah, and also anybody, if you have any questions, please feel free to raise it up. So here, I think there's some difference between task and occupations, right? You can think about occupation as a like continuum of like combination of different tasks.
Yeah.
So even we are living in like maybe on the in the scenario on the right hand side, there might be still some bottleneck tasks for in each occupation that are really hard to like automate, like interpersonal stuff, the connection and the affection people tend to build through the interpersonal relationship. If that is the case,
Yeah.
then yeah, that's possible. Even maybe that all of the tasks, nearly all of the tasks are automated, but still the the majority of jobs will be still be there because there's some bottleneck task which is important for every occupations. Really
Yeah.
hard to be automated. Yeah, that's just my one of my
Yeah,
idea.
you're absolutely right. So in this scenario on the left-hand side with the green bars, you can see that those bars, they are pretty small. They're just a small number of tasks that are not yet automated for any given level of automation. But that may be enough for human labor to maintain its value. And the specific conditions for that are what we will analyze in the paper. Yeah, next slide, please. So what are the key results? We find that the output impact of this transition depends on two important forces. And the first one are the productivity gains from automation. And the second one is the degree of capital accumulation, because you need capital to perform all these automated tasks. If we look at the wage impact, there is a third factor that is crucial, which is the degree of labor displacement from automation. So the overall effect on wages depends on a race between automation and capital accumulation. And what we argue in the paper is that this race between automation and capital accumulation is going to be one of the central forces in the 21st century. And it's going to be much more relevant than the race between education and technology that Tinbergen already described in the 60s and that Goldin and Katz wrote a book about. We argue that wages will collapse if automation outpaces capital accumulation, or if we are in a scenario where full automation is possible, the collapse will actually happen shortly before the full automation is reached, because labor will lose its special status of scarcity. Next slide, please. So I will show two graphs that kind of depict the main results in a figure. This first one is a scenario that we call the business as usual scenario, where we just automate a constant fraction of tasks, but we also leave a constant fraction of tasks unautomated every period. In some ways, you could say this is what has been happening for the past few decades or even centuries if you look at the UK. And in each of these graphs, we first show the path of output, the blue line, and then this is logarithmic. We show the return on capital or the capital share, you could say RK, which is the red area, and the wage bill, which is the green area. In this business as usual scenario where we automate a constant fraction of tasks every period, and I should also mention this is a logarithmic scale on the y-axis. So that means if we see a straight upward sloping line for output, that means exponential growth. And you can see output grows exponentially, and in tandem with output, the capital share grows roughly in the same proportion, and the wage bill grows roughly the same way. Next slide, please. However, if we consider a scenario where full automation is possible, we call this scenario our baseline AGI scenario, you can see that at first, the first 5 or 8 years look very similar to the previous graph. So output grows roughly exponentially. Wages grow, well, maybe not quite as fast, but still roughly exponentially. Yet then around year 15, as we approach full automation, two things happen. First of all, output growth really accelerates. And secondly, wages level off and start to decline. And once we have reached full automation in year 20, we kind of converge to an economy that exhibits AK-style growth, that exhibits growth solely driven by capital accumulation at a much faster rate than before. Remember, this is a logarithmic scale here. So that means you can see when the slope rises, the growth rate goes up really significantly in this economy, yet wages remain at a very low level. The next slide, please. So what I want to do now is I will first walk you through the model in which we analyze these results, and then I will show you some simulations and some extensions that I believe are also very relevant. But let me perhaps pause for a moment first and ask if anybody has questions about the general setup, the general idea of the paper. Okay, so I'll first introduce the static model environment, which is essentially a model of tasks and task automation in a similar spirit to Zera and Acemoglu and Restrepo. But the difference in our paper is that we focus on this case of full automation and what happens basically as we come very close to that and as we reach that threshold. So we assume that the kind of household side is very simple because that's not the focus of our analysis. There is a representative household who has a labor endowment of 1, and for the static environment, the capital endowment is also given, K units of capital. And then we assume that this complexity distribution of tasks, you remember the graph with the bars that I show, is described by a cumulative distribution function, CDF phi of I, where the index I depicts the level of computational complexity of each of the tasks. So in some ways, we assume that this is this one distinguishing characteristics of tasks. Some of them are computationally complex, others are computationally simple, and that's what determines when we will be able to automate a given task. Aggregate output is consists basically of a CES aggregate of all these different tasks, and we assume that sigma is less than 1. So that means all these different tasks are gross complements. We need all of them in order to produce output, which is necessary to make the whole problem interesting. Now, for each of these tasks, Y of I, in each complexity bucket, how can we produce them? Well, there's two possibilities. The first possibility is if this complexity bucket has already been automated, and we assume that there is this automation index capital I. So if little I is less than capital I, if the complexity of a given task is less than the automation index, then we can either use capital or labor interchangeably to produce this task. On the other hand, if the complexity little I is greater than our current state of automation, then we can only use labor to produce this specific task. And then we bunch up all the different tasks in the economy, that all the things that we have produced, and we obtain aggregate output Y as a result of that. Next slide, please. So what are the strategies of the household? Well, the household problem is actually really simple, right? The household just exogenously supplies their capital and labor endowment at prevailing factor prices. W is the wage and R is the return on capital. The representative firm is where all the decisions lie, but here in the static setup, things are also really simple. So the representative firm decides how much capital and how much labor to allocate to each of these basic tasks in order to produce task Y of I. So their maximization problem is to maximize profits, to maximize aggregate output minus their capital bill minus their wage bill. Next slide, please. And an equilibrium is the usual thing. It consists of an allocation of capital, of labor, a production of individual tasks, a production of aggregate output, I suppose, and then factor prices such that the maximization problem of the firm is solved and markets for capital and labor clear. So this is a very simple model. There are no market imperfections. That means the equilibrium is also the first best. Next slide, please. Now, our first important result is to identify a threshold level of automation. So remember, capital I was our automation index that determines which tasks are automated and which ones are unautomated. And what we find is that there is a threshold level for this automation index for given supplies of capital and labor, for given capital intensity of the economy, such that there are two regimes. The first one is what we call region one. If automation is not too far advanced, then we are in a regime where capital is comparatively abundant and labor is very scarce and wages are high. This is the world that we currently live in. Wages are high, returns on capital are comparatively lower. Labor is only used for the unautomated tasks because it's comparatively expensive. And production is CES according to our aggregate production function. However, if automation proceeds for given supplies of capital and labor, and if we cross this threshold level I had, then what happens is at some level, capital suddenly becomes equally scarce as labor in terms of their measured returns. So the wages and the returns to capital become equated. At the margin, for the marginal automated task, they are effective substitutes. And the economy-wide production function can be described as a linear production function. Since capital and labor are at the margin substitutes, all we care is the sum of the two, and our production function is essentially AK. Next slide, please. Here we are kind of illustrating what happens as we automate, as we move our automation index I to the right in a simple figure. So on the horizontal axis of each of these two graphs, you can see the task complexity of different tasks. And we have drawn a dotted vertical line that is labeled by capital I, which kind of delineates those tasks that can be automated and those tasks that are unautomated. What you see here is for the automatable tasks, for the tasks that are to the left of the index I, we employ capital, which is relatively cheap and abundant. So that means we employ a high level of capital. We produce quite a bit of these automated tasks because they are cheap. And for the tasks that are to the right of the automation index I, we have to use labor because they can't be automated quite yet. But since labor is comparatively scarce, we are producing less of these non-automated tasks. And total output is kind of given by the aggregate of all the tasks in the economy, the tasks we produce with capital, and the tasks we produce with labor. Now, what happens if we shift the automation index to the right? That's now depicted in the right-hand figure. So you see I shifts to I prime. That means there are suddenly more tasks that are automatable. For a given supply of capital, that means we spread our capital over more tasks. And that means each of these tasks sees less output, each of these automated tasks, because we have to spread the capital over more of them. So you see the amount of capital used for each task declines. On the other hand, there are fewer tasks that are left to labor. So that means we spread the labor over fewer tasks, and there's more labor per unautomated task. You see that second horizontal line goes up. And as our automation index increases, those two lines move closer and closer and closer together. And when they are at the same level, then capital and labor are equally scarce, and their relative returns are equated. And then we have essentially this regime change where we move from region 1 into region 2. Next slide, please. So the next thing that we look at in the paper is the factor price frontier. What is the factor price frontier? So the factor price frontier is the dual of the isoquants. It essentially depicts all possible combinations of R and W of returns to capital and returns to labor that may result from profit maximization under different ratios of capital and labor in this economy. So if the economy is very, very capital intensive for a given production technology, for a given level of automation, then there is a maximum level W star, a maximum level of wages that can be supported. And then as the capital intensity declines, we move down this factor price frontier towards this dot on the 45-degree line. So that means wages decline, the returns to capital increase as we accumulate, as labor becomes less scarce, as the capital labor ratio declines. And then what happens at this point on the 45-degree line, that's when we switch from this region 1 into the region 2, because capital and labor are now equally expensive. Their return is given by A because it's like an AK technology. And at that point, the two are effective substitutes. And we don't move further on this line. So starting from that point, we are in region 2 of the economy, and everything behaves according to the laws of an AK model. Next slide.
A small question.
Oh, yes, please.
Yeah, because the result rests on the assumption of constant elasticity of substitution. But I'm thinking that for any two different levels of computation, computational tasks, well, the elasticity between any pair of them might not equal to sigma, right? So if you imagine that for one kind of computational task, is going to be very hard, and for one kind of computational task is going to be very easy. So the elasticity between those two tasks are enormously different from the others. That is going to create a wedge of the wage, and it's going to change this nice scale, this nice wage profile. Do you understand what I'm trying to say? So if you deviate from constant elasticity of substitution, a regulatory wedge is going to create on the wage.
Yes, I think I can see what you describe. So I guess it is, kind of one of the weaknesses of these models that we assume for simplicity, for analytic simplicity, that the elasticity of substitution in such models is typically assumed to be constant. Now, I think one way I would like to think about it is imagine, like, take the lowest elasticity of substitution among your tasks.
Yeah.
And let's say that's the most conservative case. And then let's describe the whole model for the most conservative case, even though we know that some tasks are actually more substitutable than what we assumed. And then I think that will still give us very strong predictions, actually, for this conservative scenario. The numbers will be slightly different, But I think many of the insights that we get from this kind of more simple model will still carry over.
Yeah, I'm guessing that, well, the reason we see wage premiums across different industries is because the elasticity of substitution between the computational tasks are different, at least.
Different, right? Yeah, that makes sense, and I agree with that. So this is
Thank
kind
you.
of an analytic simplification that can't quite capture that, but I think it still delivers some useful lessons that help us to think about these different elasticity of substitution scenarios as well. Thank you.
Yeah, thank you.
Next slide, please. So this just says exactly the same thing analytically. It says that, well, there's this downward sloping factor price frontier, but once we reach the 45-degree line, it becomes degenerate and the returns to capital and labor are equated. Next slide, please. Now, what happens if productivity goes up, if the A in our production function goes up? We just scale the whole factor price frontier proportionately out. Next slide, please. And what happens if our level of automation changes? If we increase the automation index, let's say we start such that nothing is automated and we crank up the automation index until everything is automated, or until we reach this region 2. Well, there is a path in this space of factor prices, which we call the path of automation and what you can see here is, at first, if we have nothing automated, we are essentially in an AL economy. So it means the return to wages is equal to A. Then if we automate a little bit, wages rise rapidly at first. Then that increase in wages kind of levels off for a given supply of capital and labor. And then wages start to decline again, until eventually we hit the 45-degree line in this space. Next slide, please. So, we show that automation always raises output as long as capital is abundant, because if capital is no longer abundant, it doesn't help you to automate things. And secondly, we show that the effect of automation on wages is this hump-shaped effect. There's at first a productivity effect and then a displacement effect. Next slide, please. And with that, that basically concludes our description of the static setup. So the next thing, which is where it gets really interesting, is if we introduce dynamics into the setup. Because in practice, capital is, of course, not given, but capital is accumulated over time. So the first thing we need to assume is we need to make assumptions about all the exogenous elements of the dynamic model. So we assume that this automation index I just kind of grows exogenously, and it grows exponentially, reflecting things like Moore's law. And then we identify how the dynamics of output and wages are affected by this interplay of task automation, which depends on this distribution function for task complexity that we assumed, and the force of capital accumulation. Next slide, please. So we assume a kind of standard Ramsey setup. We have this representative household that intertemporally maximizes utility of consumption, subject to a standard law of motion for capital. And the only thing that differs from the standard Ramsey setup is that you see in this production function here, there's our automation index IT, which grows exogenously over time.
Another small question.
Yeah, please.
I'm trying to thinking that if you add labor heterogeneity, for example, task-intensive labor and non-task-intensive labor, that is still, for example, if the task-intensive labor, the labor market for this kind of human capital is not cleared, we are always on a shortage of the supply of this high quality labor, then will the wage keep going down?
Yeah, so we look at an extension in which we assume that labor is kind of heterogeneous,
Yeah.
and that different types of labor can perform tasks of different complexity. And then it turns out that within each of these buckets of labor, we can identify whether we are in this region 1, where labor is scarce, or region 2, where labor and capital are effective substitutes. And the dynamics are very much driven by that, but in a more fine-grained kind of manner. If we have time to get to that extension, I will say a little bit more about it, if that's okay.
Yeah, because the labor dynamics, what I'm trying to say is that, well, for the labor that has been replaced by AGI, those kind of labor market, this labor market is gonna get cleared, and for the other market, well, it might not get cleared all the time, and if it has a labor shortage on the task intensive labor, then it's gonna give you a different dynamics of the wage. This is what I'm trying to say.
I think I can see that, and that makes a lot of sense. I'll say in this model here, we assume that markets are always
labor
clear,
markets gets cleared all the time.
Simplicity. Right? But I guess the interesting thing is that once we are in this world with heterogeneous labor that can perform tasks of different complexity, what you see is that the automated labor sees its return collapse. And in practice, oftentimes that would be associated with unemployment and non-market clearing. And the non-automated labor is going to become more and more valuable. So there's going to be a smaller and smaller fraction of the population that will reap more and more of the returns to labor. And I guess in practice, when you have these really rapidly rising wages for a small segment of the population, people would perceive that as, oh, there is a labor shortage, right? And in a market clearing setup, we just see the wages kind of skyrocketing.
I see. Thank you.
Thank you. Next slide, please. So the next thing we do is we show that we can actually identify lower bounds and upper bounds for capital accumulation, for output, and for wages. And those upper bounds hold no matter what the savings behavior of our agent is, as long as it is some sort of optimizing savings behavior. The lower bound is given by the case in which we just don't accumulate any extra capital. The upper bound is given by the case where we accumulate so much capital, so much extra capital, that the return on capital is pinned down by our rate of time preference plus depreciation. Next slide, please. And we start with some analytic results about these bounds, because if we can characterize the bounds, that gives us kind of very general lessons that are independent of any specific simulation. So the first thing we show is that this lower bound for wages at first rises as we automate, and then it comes down. The second thing we show is that the lower bound on the wage always declines to A, to our level of technology, if full automation is reached asymptotically. And then the third thing we show is that the upper bounds, they are all increasing in how much automation we have. However, if we reach full automation, essentially if we reach AGI, then the upper bounds of capital and output are infinity. That means the economy can just explode. But the upper bound on the wages discontinuously collapses to A at that point where we reach AGI. So if we are an epsilon before AGI, the upper bound to wages converges to infinity. But the moment we go from AGI minus epsilon to AGI, it discontinuously collapses to A. Next slide, please. And I can tell you more about the intuition of that kind of in a couple of simulations. So again, what's the exogenous thing that we feed into these simulations? The first thing is we feed in a task complexity distribution. So here you can see 4 different scenarios for how tasks are being automated. And in particular, the vertical axis in each of these graphs shows you the number of, or the fraction of unautomated tasks in the economy. In this business as usual scenario, we assumed that a fixed fraction of tasks is automated. So this is exponential decline, right? And on a log scale that shows up as a linear curve going down. Then we assume a baseline AGI scenario in which you can see we automate, and then at year 20, the fraction of unautomated tasks essentially drops to 0. On a log scale, it just means it drops through the bottom. The third scenario is what we call an aggressive AGI scenario. This is if we take some of the predictions made by technologists seriously, that we may actually reach this level of full automation within 5 years from now. And you can see here, yeah, the fraction of unautomated tasks drops through the bottom at year 5. And then finally, we assume a mixed scenario as our last case. In this mixed scenario, we assume there's a lot of automation in the first 5 years. For example, imagine we are automating all the cognitive tasks, all the tasks that white-collar workers are currently performing. But we assume that there is like a very small fraction of tasks that we are just not automating, or that we are not letting the machines automate. So imagine these are like regulators, these are alignment workers, or maybe they are like spiritual workers, or who knows what. So we assume there's first this rapid task automation. The fraction of unautomated tasks really drops quickly until year 5. And then after that, we are in something similar to the business as usual scenario, where we just automate a constant fraction of these remaining tasks every year. So those are our 4 scenarios, and that's what we feed into our simulation. And
yeah, sorry, may I ask a question? Could you clarify what kind of parameters that determines the 4 scenarios? Just the distribution of complexity of tasks, or there are other parameters?
Yes, so for these 4 scenarios are essentially what differs between the 4 simulations that I will show you in a moment. And these 4 scenarios that you can see here, they are exogenously fed into the model.
Then could you give some, I mean, rough description of what a distribution would be like for the 4 scenarios?
Oh, yeah, sure. So analytically, the first scenario is simply exponential decline of unautomated tasks. So it's a standard exponential distribution, or if you want, it's a Pareto distribution in the space of task complexity. Then the second and third distributions are beta distributions, because beta distributions have this kind of bounded nature. The first one is stretched out over 20 years, the second one stretched over 5 years. And then the fourth scenario is actually a mixture of the first and the third. So it's a mixture of an exponential distribution and a beta distribution. Okay.
So, yeah. Just I mean, a rough question. Which one would you think is more realistic?
Yeah, that's the $1 million question, right? You know, so I personally, I kind of vacillate between the aggressive and baseline AGI scenarios, but I also think that there's an important social factor. As one of the commenters has kind of emphasized before, we may choose not to let everything be automated, and then that would give rise to something like the mixed scenario. But yeah, I think part of the reason why we all should look at different scenarios is because there's so much uncertainty about this, right? And that's why I would really feel that each of these scenarios is quite plausible. And I'm on a record. I've published like a piece with the IMF where I say I think each of these scenarios has at least 10% probability. So I take them very seriously. And you may wonder, why did I choose 5 years and 20 years? That's actually based off a quote by Geoffrey Hinton, who he observed, and that was actually already a year ago, that he could imagine that we'll reach AGI anywhere between 5 and 20 years. So, you know, since he said it a year ago, maybe we should say 4 to 19 years now, but I thought 5 to 20 is a bit crisper. And yeah, he was the godfather of deep learning. So I thought it makes sense to pay some attention to his prediction here.
I guess one of the most important takeaways for me from this paper is that complexity of tasks matters, or a distribution of it matters. Then the question would be, what determines the complexity, and how can we try to approach that question?
Yeah, I think ultimately it's the computational complexity that matters. And we humans, we didn't quite appreciate that some things that we thought are so complex are actually not that complex. Like when we interact with large language models, I guess one of the lessons is that generating text, and even generating text that has some meaning, was not as complex as we thought it was. And then I guess one of the lessons of Moravec's paradox is that navigating in the physical world is a little bit more complex than we appreciated 30 years ago, but we are making rapid progress on that challenge as well, from what I understand.
I agree, but I would think perhaps there's more than just computational complexity, because the key actually is the substitution between labor and automation, right?
Yeah.
Yeah. So it's not.
If you take it for granted that computational complexity is what matters, then yeah, the machines can compute things, and human brains are, if you take a perspective from information theory, human brains compute, right? We receive signals through our eyes, ears, all our nervous system. We have information encoded in our brain, and no matter if we engage in, let's say, creative tasks or emotional intelligence, or all these things that we always thought define us as humans, our brain is still processing signals, and our brain is performing computation. And so that's essentially the philosophical perspective from the paper is coming.
Yeah, if we assume that everything can be modeled as in an information space, then that's true.
Yeah, and my understanding is modern neuroscience thinks about brains in that way.
Thanks for the tip. Thank you.
Next slide, please. So now let's focus on this race between automation and capital accumulation. What determines the dynamics of wages? So to get a nice analytic result, it's sometimes useful to look at like knife edge cases, right? So we look at the threshold where the wage effect of automation and capital accumulations offset each other. So in other words, we want to look at the case where wages are unchanging because what we save, what we accumulate in terms of capital precisely offsets what we lose from automation. So you can see this in this equation that's in the center of the slide here. On the left-hand side, we have how much we save, S times Y, times how much that affects the marginal product of labor, which is FLK or FKL. And the effect of additional savings on wages is precisely offset by the effect of automation, which is this advancement in our automation index and how far to the right we move in our distribution function phi. So how much does an increase in phi affect FL, the marginal product of labor? And then we can characterize this level where savings precisely offset the effect of automation, and we get to a balancing savings rate given the growth rate in the automation index G and given our task complexity distribution phi. And this balancing savings rate here consists of a whole bunch of elements. Next slide, please. So you can see first it consists of a displacement effect, which means that we need to save more to kind of catch up with the negative effect on wages. Then it consists of a productivity effect, which means we don't need to save as much because we are more productive, and that raises wages. Next slide, please. It also depends on the capital intensity of the economy. We need to save more if we have already more capital. And then next slide. It depends on the kind of point mass of tasks being automated at any given time. And next slide. And finally, it depends on the speed of progress in our automation index. So this allows us to kind of delineate what savings rate in an economy would precisely offset the effects of automation. Next slide. I think I have to speed up a little bit now because we are approaching the end of the hour. But yeah, analytically, it turns out that we can actually find a very nice result if the distribution of tasks in complexity space is Pareto, and if the economy starts in a region 1 where labor still has its special status. So if task complexity is Pareto, that means we always have a tail of unautomatable tasks. And still, there are 3 scenarios for what could happen to wages. First of all, in case 1 here, if the automation rate G times the Pareto parameter for this task complexity distribution, if that's too large, then wages collapse to A and the labor share converges to 0 in this economy, even though there is always this thin task of this thin tail of unautomated tasks in the complexity distribution. The second case is if the speed of progress is at some intermediate level, then wages grow exponentially at a certain asymptotic rate, and the labor share actually converges to 1. So again, we have a Pareto tail of unautomated tasks, but it is thicker now. And as a result of that, wages will always grow, and ultimately labor will earn all the returns to the economy. And lastly, if the rate of progress, the rate of automation, lambda G, is small, then wages will also grow exponentially, but not quite as fast. And the labor share will converge to an interior level between 0 and 1. So again, in all 3 of these cases, we have a Pareto tail of unautomatable tasks. But depending on how thick that tail is, wages may either collapse or just continue to skyrocket. Next slide, please. So now I'll show you the basically output and labor effects of the 4 scenarios that we depicted before. In the business as usual scenario, and we have already discussed that, we have exponential growth in output, exponential growth in the capital returns, and exponential growth in the wage bill. Next slide. In the AGI scenarios, we will end up with a collapse in wages. And since we identified this region 1 and 2, it turns out that that collapse may actually happen before we reach full AGI. So let's look at our simulations for that. Next slide. This is the baseline AGI scenario in which you can see what we already discussed before. Output growth really speeds up, wages collapse. Next slide. In the aggressive AGI scenario, output grows much faster even in the short term, wages collapse even sooner. Next slide. And then in this kind of mixed scenario, something really interesting happens. Wages at first collapse to A because we move from region 1 to region 2 of the economy, where labor loses its scarcity value. So we have seen a lot of automation in very quick succession. And as a result of that, labor is no longer special, and it's actually, we have a shortage of capital. If you want, we have a shortage of robots, a shortage of chips, and so on and so forth. And labor is relatively abundant. We use labor for things that could be done by machines because we don't have enough machines. And the interesting thing is, in this mixed scenario, we assumed that there was this thin tail of unautomatable tasks, right? So what happens here after the collapse in year 5, the economy continues to grow, it continues to accumulate capital, and eventually we have enough capital again that we move from region 2 back into region 1. And from that point forward, wages and output grow roughly exponentially again. And so that means the wage bill recovers and workers' returns go up significantly. So this tells us that if there is a short-term bout of automation, this may really hit labor markets hard. This may look terrible for labor, even though there are still unautomated things, and ultimately things turn out quite well for labor. Thank you. Next slide, please. Now I have a couple of extensions, and I think next slide, please. I'll just quickly jump over those. Next slide. So first, we assume that there are some other fixed factors. In our baseline model, we had capital and labor, and once labor can be automated, everything is accumulable factors. Here in this simulation, we assume that minerals or matter or whatever are a fixed factor that's in finite supply and that cannot be automated away. And if that happens, then the wage bill always declines, and these fixed factors gobble up more and more of their returns. Next slide, to the next figure, please. Yes, thank you. And another more rosy outcome is if we can also automate technological progress, if we endogenize this productivity parameter A, and we assume that these new machines can not only automate the production of output, but also the production of knowledge, then output can actually take off, and we observe the same result that was also observed by a paper by AGI et al., that there may be a technological singularity here in this particular simulation. It occurs in 12 years. And I think now we just have time to jump to the very last slide, because we are at the full hour. So what we have shown in this paper is rapid automation may fundamentally change the structure of the economy. We may switch from this region 1 where labor was scarce in region 2 where it's not. And that fate of labor would be the biggest concern in such an economy. It will be determined by a race between automation and capital accumulation, but under AGI, labor will lose the race. And this may happen even before AGI if we have a bout of rapid automation. And what's the silver lining? What's the positive message? Well, there will be a growth takeoff under AGI, and that should make it possible to compensate the workers that lose out, so that ultimately everybody is better off from these amazing technological advances. And the big question is, will we succeed in doing so? I very much hope we will. Thank you.
Okay, so thanks, Anton, for this insightful talk. I think we still can accommodate 2 or 3 questions or 1 or 2 questions, if there's any from audience.
Yeah, if anybody needs to jump off, I perfectly understand, because we are past my time, but I'm very happy to stay on for a few more minutes.
Long, please.
So, yeah. Okay. So, it's my opportunity to ask a question.
Yes, go ahead.
Okay, so
sure, go ahead.
thank you, Anton. I'm a graduate student who's majoring in economic and also fascinated by the development of AGI. Before the lecture began, I used ChatGPT and spent 2 hours trying to get a preliminary understanding of your paper. I'm very grateful for your contribution. To be honest, it's one of the most exciting paper I have ever read. So I prepared 3 questions I would like to ask you, but I don't know if time allowed. But let me present my questions first. My first question is that you mentioned that the computational complexity is based on the task definition, but AGI uses end-to-end algorithm during the training process. Does this mean that its complexity cannot be measured by the complexity under the diving and conquer method? That's my first question. My second question is, should the output brought by AGI be understood as labor or capital? I understand that the development of AGI as a process of intellectual accumulation. Therefore, like wage growth brought about education or skill improvement, can the efficiency improved by AGI be considered part of wages? For example, if an economist can increase the number of papers published tenfold with AGI, but the increase would still be in their salaries, right? My third question is, furthermore, considering that the computational power required by LLM trainings is hundreds to thousands of times greater than for inference, can we further distinguish training as capital accumulation and inference as labor compensation? That's all about my 3 questions.
Let me try to give a quick reaction to each of them. So one way of thinking about measuring computational complexity is to just use this number of floating point operations to perform something. And training a frontier AI model takes a huge number of flops, floating point operations. Doing inference takes, as you say, a lot less compute. And at some level, I have to admit, the model cannot quite literally be carried over because we have this fixed cost versus variable cost problem. But I think how we measure that complexity in machines is pretty straightforward because we just look at these flops. How we measure it in humans is a little harder because, first of all, our brain can usually do only like one or a small number of things at once. And our brain operates even if we use only a small part of it, right? Is AGI labor or capital? Well, the way I would look at it is effectively the distinction becomes irrelevant. Labor is just a different form of compute when we reach region 2 in our model here. And so you can say the model where we had capital and labor was a really good model of the industrial age of what started in Great Britain around 1800. Before that, it wasn't a good model because before that, the Malthusian model worked much better. We had land and labor, and that's what best described the economy. And maybe, in the age of AI, this distinction of capital and labor is no longer really relevant because labor won't be relevant. Now, you asked, will the productivity increase if you can write 10 papers using language models, go to you, or will it go to the AI? Well, let me ask back, why would it take you to write those papers? Why can't the AGI write them autonomously?
Well, to be honest, that's something I'm very concerned that I don't know whether my professor still need me when he has ChatGPT.
And whether we professors will still be needed, right? Those are some of these really difficult questions.
Yes.
And training versus inference. Yeah, I think we already kind of discussed that when we talked about capital and labor. It may not be a useful distinction anymore in the age of AI.
Hello.
Please go ahead.
Hi, Anton. This is Long Chan from Luohan Academy. Thanks for the interesting speech. And I have several comments.
Yeah.
The first comment is that I think historically, automation for all the jobs, it has been proven to be very difficult. And this is why many industries are still labor intensive, especially the service industry. And so, and also automation is only part of the jobs in the industry. And I've been talking to entrepreneurs that are trying to make their machines just like Elon Musk does in his factories to help them to gain kind of the general capacities, can solve multiple problems, the jobs. But then I think my point is that automation is difficult, and when you make this general, and also think about the management, integration of the jobs, judgment. And I think another thing we've seen in the past, the lesson we've learned is a failure of the smart contract, facing uncertainty. And I think Ben Holmstrom and I had a very lengthy discussion on this. It's being overstated. My first point is that fully automation stuff like that, it probably is a little bit overstated. I'm trying to guess. My second point is that we probably want to be a little bit careful to say labor is just computing power. Now, I think the key is to understand and define the complexity of jobs. And one interesting observation is that machines are not human. For example, they do not have many behaviors, features, and preferences like humans do. And these have good or bad. They're just different labors and different organizations that leave rooms for people. My point is that there's a limitation of saying that it's just computing power. It's probably more complex than this. But I think the key is to define what is the job, what is a human does job, and what's different from the machine does job. I think they're different in many ways. But finally, I'm trying to, and your paper does force me to think about what is more realistic. I think there are several things probably. That's my takeaway. You can tell me I'm wrong. Firstly, I think more people will be thrown into service. That will speed up that process. We can tell that, including the white collar jobs. And I think another thing is certainty is that we will see more general jobs better done by machines, but that doesn't make them human. And that does leave room for human because they're different from humans. So that's my guess of this. And also there's a social factor, as you mentioned a bit. I think Elon Musk also mentioned a bit that we can define and leave space for the human considerations for them. And finally, I do agree with you that fast changes will happen in certain industries, but I also believe that most likely the path will your concern. Most likely that path will not happen. That's my take on this.
Well, thank you very much for these, I have to say, really thoughtful and deep comments. It is difficult for me to do justice to them in just 2 minutes, but let me try my best. So first, I want to say I fully agree with your description of what happened historically. I also want to warn all of us that maybe this time is actually different. Nobody knows. That's part of why I advocate scenario planning. The second point is, I think I very much agree that at least in the short term, let's say short to medium term, there's going to be this small set of tasks that we will probably reserve for us humans, and maybe even tasks that the machines can perfectly well accomplish. Like, let's say, we are economists, let's say setting economic policy. Maybe in 5 years, we have an AGI that could do a very decent job setting economic policy, but maybe we'll still want to be involved as humans because it's a high stakes thing, and handing over high stakes things to machines is something we want to be really careful with, right? So I think one takeaway of mine is that these scenarios where we are very close to full automation, but not quite there, are really interesting scenarios to study. And that's why we focus so much in the paper on kind of characterizing the results. What happens if there is this small Pareto tail of unautomated tasks? What happens if the tail is a little thicker or if it's a little thinner? I think that may be the kind of world that we will find ourselves in a few years. And yeah, I guess regarding your predictions, I can only say
we'll see.
Those are very interesting and very thoughtful, and I'll have
I
to
just
spend
think
more
that
time thinking about
it's
them.
good for you to define, to think about those things. But
Yeah,
I
yeah.
think how do we distinguish what is more likely? I think we have to go back and define job done by human being, and it's job and it's also human being. And then now the machines coming in. So do they really substitute? What can they really substitute, and what they cannot? And so
Right.
I think that's how we can distinguish, my guess.
I very much agree, and I think there are several forces that have surprised me in the last 2 years or so. I guess one force is I have been surprised at the slow take-up of, let's say, for example, generative AI. But at the same time, I've been surprised at the progress in terms of technical capabilities, even accelerating. So it's this very funny world where, on the one hand, these machines are getting so much smarter. On the other hand, the actual real-world impact so far isn't actually
exactly. So that goes back to why we need to understand the nature of this thing, because in the internet age, I mean, I've been observing in the internet age globally, many startups made a lot of mistakes. They're pouring monies into a blockchain to many areas, but it's just I think they somehow underappreciate the nature of the industry or stuff like that. So, but exactly as you mentioned.
Yeah, I'll say in the internet boom, I think nobody talked about that it may be possible to automate us entirely away. And nowadays there are technologists who say, well, look, these machines, they may be able to do exactly what our brain can do. And in that sense, it may be different.
It's different.
Yeah.
Well, we don't know.
A lot of uncertainty.
Right. Thanks.
Thank you.
Hi, Professor Anton. Can you hear me? Yes, thank you for this very beautiful macro model with AGI scenario. So I have a small question, but it's a bit from the micro side. I want to hear what's your perspective on this, because after I read your paper on AGI, I can't help but wondering that if we put this AI adoption question in the context of a two-sided contracting, like between the investor, principal, and these agents. So, what do you think? is the key trade-off if in this contract we are thinking about, you know, an AI adoption choice in this contracting? For instance, if the principal want to adopt an AI technology, and as in your paper, you mentioned a mechanism that's going to replace these agents, right? So I wonder what is the difference between, you know, if we compare this situation, this AI adoption versus the situation that, you know, if a firm is going to, you know, have an acquisition that's going to replace the agent itself. So they both have the similarity that, you know, the CEO got replaced, right, due to a different scenario like AI adoption or this, you know, firm acquisition or merger situation. They can increase perhaps the firm value, but these agents going to get replaced. I just wondering, you know, what is the difference from your perspective? Yeah.
Yeah, I don't know if I have a good answer to this one, but I guess my impression is that these systems are themselves becoming more and more agentic, as you say, and eventually, when we think, for example, of the actors, of the decision makers in the economy, who makes all the calls, both on the investing side and on the production side, and ultimately consumption side too. I wonder if that's all going to be more and more the AIs. Now, I don't know how to best translate that into your framework.
Interesting. Thank you, Professor Anton. I'm gonna keep working on this. Thank you.
So work in all of these areas is very, very important.
Yeah, thank you.
Yeah, I guess we already about 20 minutes past. So thanks again for everyone. Thanks again for Professor Anton Korinek for this wonderful talk. And thanks everyone for coming in today and ask very insightful questions. Thank you a lot, and hope to see you soon in our future webinars. Thank you.
Thank
Bye.
you very much. Bye, everybody.
Thank you. Bye.